For as long as we've had cars, safety has always been about the nuts and bolts, right? Making sure the brakes don't fail or the engine doesn't seize. But we're in a totally new era now, an era where safety isn't just about preventing things from breaking, it's about understanding the complex and, let's be honest, sometimes really weird decisions that a car's AI makes. And that is exactly what we're going to unpack. So let's start with the big question, the one that changes everything. Imagine a crash. The investigators get there, they look at the wreckage, and they find nothing. The brakes were perfect, the steering was flawless, the software had zero bugs. Every single sensor was working exactly the way it was designed to. So what in the world went wrong? And believe me, this isn't just a thought experiment. This is a real-life scenario that tragically led to a fatal accident. The car's camera system, which was working perfectly, was just fooled. It was a tricky lighting condition that our brains can handle, but the AI couldn't. This is the new frontier of car safety, where the real danger isn't a broken part, but a limitation in how the car sees the world. Now, to really get our heads around this, engineers have come up with two completely different ways of thinking about safety. You've got the way we've done it for 100 years, and then you have this whole new philosophy that's built for the age of AI. So on one side, you have the classic standard ISO 2662. That's all about what we call functional safety. And on the other side, you've got the new kid on the block, ISO 21448, which is known as SOTIF. Now, SOTIF stands for Safety of the Intended Functionality, which, yeah, is a total mouthful, I know. But the idea behind it is actually pretty brilliant.
And here is the absolute best way to understand the difference. Think of functional safety as the car's health. It's there to prevent a mechanical heart attack, like a power steering failure or a computer chip error. But SOTIF, that's all about the car's skill. I mean, a perfectly healthy human driver can still make a critical mistake in heavy fog or on a slick, icy road. SOTIF is about making sure the AI is skilled enough to handle the chaos of the real world.
And that difference changes the fundamental question engineers have to ask. Functional safety asks, what if a part breaks? But SOTIF asks a much, much trickier question. Why did it crash when every single part was working perfectly? The risk isn't coming from a system failure. It's coming from a performance limitation. The system just wasn't good enough for that one specific, crucial moment. Okay, so how can a system that's both healthy and supposedly skilled still get something so wrong? Well, to figure that out, we have to perform an autopsy on the AI's thought process. And it all breaks down into 3 simple steps: sense, plan, and act. It always starts here, with how the car actually perceives the world around it. Its sensors are its eyes and its ears, but just like our eyes and ears, they can be fooled. This is ground zero for most of these strange SOTIF issues. And the real-world examples are just fascinating. A car's radar can bounce off a metal manhole cover and create a ghost target out of thin air, causing the car to slam on the brakes for absolutely no reason. A camera can be completely blinded by sun glare coming out of a tunnel. And LiDAR, the laser system, can mistake the steam from another car's exhaust on a cold day for a solid wall. And in every single one of these cases, the sensor is working perfectly. It's just physics getting in the way. All right, but let's say the car does see the world perfectly. What then? Well, believe it or not, its own logic can still get it into a whole lot of trouble. This is the planning phase.
So picture this. 4 self-driving cars pull up to a 4-way stop at the exact same time. Their programming says, be safe, be polite, let the other guy go first. So what happens? They all just sit there, waiting for each other forever. It's a digital standoff. Or you have the freezing robot problem, where in a crowded city street, the car calculates that any movement carries a tiny risk, so the safest possible thing to do is to just stop, right in the middle of traffic. These aren't bugs in the code, they're the logical and very frustrating result of safety-first programming.
And finally, we get to the act phase. Because even if you have perfect sensors and a brilliant plan, the way the car physically carries out a command can create its own brand of unexpected risk. It's something called the ping-pong effect. The lane-keeping system sees the car drift a tiny bit to the left, so it corrects to the right. But because of a minuscule delay, it overcorrects. So now it has to correct back to the left, and back and forth it goes. The car starts to sort of oscillate in the lane. Again, nothing is broken. It's just a tiny little imperfection in the control algorithm that can feel really, really unsettling if you're behind the wheel. So, if these problems are so subtle and so bizarre, how on earth do engineers even begin to find them before they cause an accident out on the road? Well, this is where the hunt for hidden dangers really begins. So engineers divide every possible driving scenario into 4 big buckets, but the one they are completely obsessed with is Area 3, the unknown unsafe. You can think of this as the dark matter of car crashes. These are the bizarre, unpredictable edge cases that nobody has even imagined yet. The entire goal of SOTIF is to explore this dark space and, piece by piece, shrink it down to nothing. And they do it with a constant 3-step cycle. First, they explore, using these massive computer simulations and real-world tests to find new risks. As soon as a new danger is found, they define it, and it moves into the known unsafe bucket. And finally, they engineer a fix and solve it, moving that scenario into the safe zone. It's just this relentless, never-ending process of discovery. But there's one wild card in all of this, one factor that you just can't always predict in a simulation, and that, of course, is us, the human driver. Which brings us to a perfect and honestly almost comical example of what engineers call reasonably foreseeable misuse. It's famously known as the orange trick. You see, to make sure you're paying attention, a lot of these cars have a sensor that detects the tiny bit of force, the torque, from your hands on the wheel. Well, people figured out you could just wedge an orange or a water bottle into the steering wheel. The weight is just enough to fool the sensor. The car thinks you're holding on, even if you're in the back seat. So now engineers literally have to design systems to defeat this kind of creative workaround. And it goes way beyond deliberate tricks. You have things like mode confusion, where a driver honestly thinks the car is an autopilot when it's not. Or even worse, there's overtrust. This was a huge factor in that tragic Uber crash back in 2018, where the safety driver was watching a show on their phone, completely trusting a system that was still very much in development. That trust was, unfortunately, completely misplaced.
So, where does all of this leave us? It really signals a profound, fundamental change in what automotive safety even means anymore.
When you boil it all down, this entire complex challenge really comes down to a simple number: 2. 2 critical pieces of the safety puzzle that absolutely have to fit together perfectly. And this, right here, is the crucial shift in thinking. For 100 years, safety meant building the system right. In other words, making sure no parts fail. But today, SOTIF demands that we also focus on building the right system, one that is skilled and tough enough to handle the messy, chaotic, unpredictable reality of our world. Which leaves us with one last, really provocative question. When a car that is, by every technical measure, working perfectly, still causes an accident, who's really at fault? Is it the programmer, the car company, the driver who trusted it too much? The truth is, the answer is no longer that simple.